Welcome viewers. In this video we are going to do design of a transmission line tower foundation type 1 pad and chimney using Indian standard. This is part 3 of 5. In our previous part, that is in part 2, we had discussed about check for bearing capacity, and before that the part 1 is covered tower geometry, design foundation loads, soil parameters, foundation geometry, and finally with the uplift resistant check we had completed the part 1. Then part 2 is for bearing capacity check. This is part 3. In this we are going to do check for sliding and overturning. Followed by this video we are going to do design of chimney in the part 4, and in the part 5 it is a design of a base slab. So with this entire 5 parts of video will cover the design of transmission line tower foundation for type 1 pad and chimney using Indian standard. Now let me go into detail about the Excel calculation. So before going to watch this video, we request you to watch our previous video part 1 and 2, and also one more video regarding the design of stub angle in American standard also explained in our previous video. All these video links are given in the descriptions. You can refer those before coming to watch this part 3. Let me go to the Excel calculation. So in the screen you can see an Excel sheet which is the calculation which we are doing the foundation design for type 1 pad and chimney. So far we had discussed in part 1 about tower geometry, design foundation loads, subsoil parameter, foundation geometry, uplift resistance check. Followed by that part 1 video. In part 2 we had discussed about how to do check for bearing capacity for the foundation for transmission line tower, and in this part we are going to discuss about how to do the check for sliding and check for overturning. These two parameters we are going to do in this part 3 video. Followed by that, next video will be the design of chimney in part 4, and the design of base slab we will be looking into that final part, that is part 5. With that, the entire foundation design calculation for transmission line tower type 1 pad and chimney get completed. Let me see this check for sliding. For check for sliding there are two methods or two way to check this. One is entire weight of concrete and weight of the soil we need to calculate, and that we need to multiply it with the internal friction coefficient. So in order to find the lateral shear resisting force from the subsoil and the concrete, so from that we need to divide those value with the actual thrust from the actual horizontal thrust from the structure. If the factor is more than 1, then we can call it as safe. Alternative method is we need to consider only the soil passive earth pressure. With that we need to check with the lateral structural thrust from the structural base. So we are going to calculate with the second method, which is more critical compared to the first one. So let me see how to do this check for sliding with the second approach. As per the Newton's third law, every action there is equal and opposite reactions in order to state of equilibrium of any object. So here we need to check those. So these are the 4 earth pressure forces we are going to calculate in order to restore the foundation against the lateral thrust which is coming from the structure in terms of sliding. So F1, F2, F3, F4 is nothing but the force which is act in the various level of foundation by the passive earth pressure. Here you can see the foundation geometry. In the right hand side you can see the dry soil and wet soil passive earth pressure coefficient or passive earth pressure which we had calculated already in kg per meter square. So there are 4 stages, 1, 2, 3, 4 in both wet and dry soil. So that is why we are having F4, F1, F2, F3, F4. So we can shrink this Excel calculation to only look for the check for sliding. So this bearing pressure is not required right now, which we already discussed, so you can shrink this. And also this uplift resistance also we already see. Okay, so now F1 for calculating the force, passive earth force around the foundation. For F1 means this part, the first triangle we need to calculate. So we know the triangle formula is half into BH. So in that half into BH we need to multiply the pressure value also in kg per meter square. So here you can see half is nothing but the coefficient for the triangle, and 0.7 is a B, that is breadth which are going to which are going to expose to the soil. So here in this first level of triangle, only this chimney is going to expose. So 0.7 meter is the breadth, and height is nothing but it is a 2.4 meter, which is a clear height from the top of the drop slab to the chimney or to the ground level. So this 2.4 is the level. So here we are marking various level according to the pressure diagram. So 0.2 is the drop thickness, and 0.25 is the trapezoidal thickness of the base slab, and 0.1 is the flat or vertical thickness of the base slab. So in the first triangle, half into BH into pressure, we are having 7402 kg. For wet condition also similarly we need to consider this pressure 4406. So it is 3701. Next F2 is a trapezoidal. So in this trapezoidal we need to consider the average of these two pressure. Again it is average means half into these two pressure summation into here that 1.5 meter is this part, this portion we need to consider 1.5 meter for the depth of 0.2. So that is why consider here 1.5 into 0.2 into average earth pressure, that is half of this two summation. So we are getting 1432 for dry condition and 716 for wet condition. Next F3 is, here in the case we are having a inclination or a triangle part or frustum here. So for this we need to take again average of this top and bottom width and average of these two pressures 10464 and 9546. So that is what considered here. So you can see that 4 meter is this edge to this edge and 5 meter is this to this edge. So average of these two we are considering 4 plus 5 divided by 2 into the thickness is 0.25, and average of this 9456 plus 10464 divided by these two, half we are considering in the initially itself, because this is a trapezoidal section. So applying this 11,256 is the value for dry and 5628 is the wet condition value. And the final one is F4, this part, the bottom part. So here again it is a vertical triangle. So this portion alone we need to consider as a exposed area to soil. So this is half into 5 meter is a total span, and 0.1 meter is a depth, and average of these two we need to consider as it is a trapezoidal. 5324 is the high density passive earth pressure, and 262 is a wet passive earth pressure. Now factor of safety we need to consider. So this is a resisting shear force which we had calculated just now, and this should be 1 2. So this we are going to check with the dry condition. So dry condition 25413 is the total shear force or passive earth pressure forces, and this 9166 is nothing but the side thrust, maximum of both lateral and transverse side thrust, which is factored. So this resistance force divided by actual thrust, we are getting 2.77, which is greater than 1, then this is safe. Similar like for broken wire condition also, we are already having this value 2743 and 2453 in transverse and longitudinal side thrust respectively. So the maximum one we are considering 2743, which we are getting the factor as 9.26. This is greater than 1, then it is safe. Similar like for wet condition also we need to check. 12707 is the total passive resistance force, and here 9166 is again the same like dry condition. So here the factor is 1.39, which is greater than 1, and 4.63 for a broken wire condition, which is also greater than 1. Hence these two also safe. Here we can see the most critical case is wet condition soil with the side thrust is a more critical, which is having nearer or just above the required factor 1. So this is what the sliding check about. Alternatively, there is another method of sliding check, which we already told, that we need to calculate the entire weight of the concrete weight and the soil weight, and multiplying those with the internal friction coefficient to arrive the horizontal shear resistance. So that will be this value under both the condition wet and dry. So that divided by the thrust force will be getting the resistance factor, which should be greater than 1. Hence we can call it as safe. Why we are not doing that is the concrete weight is heavier. Also, if we are considering the soil weight also, that case will not be a critical one. Only this sliding, this case is a more critical. So that's why we are considering this. Even for most of the transmission line tower, it is better to consider only the passive earth pressure coefficient along with that force to check for sliding. Next we can go for check for overturning. For overturning check, we need to calculate the resultant side thrust. The resultant side thrust is nothing but it is a square root of summation of squares of both the direction side thrust. So square root of side thrust T square plus side thrust longitudinal will give you the value of 12,565. Similar like for broken wire condition also we need to calculate like this. The value is 3680, and the total overturning moment you can see in the right hand side pictures with animations. So there are three forces which will cause the overturning moment. So the two forces which is from the structure, uplift and the side thrust, will cause a clockwise movement at the toe, whereas the weight of concrete will cause the anti-clockwise movement. So here is that calculation detail. So this 64841 is nothing but the uplift force from the structure, that divided by the true length will give you the verticality of the force. So 1.0313. So that was done here. So now this force will be transferred into vertical direction instead of inclination with respect to the longitudinal, with respect to the leg of the structure, and that should be multiplied with 1/3 of the base slab width. We will be getting the moment due to this uplift. Second one is side thrust. The moment due to side thrust we need to multiply. So we had calculated here the resultant side thrust, considering the both longitudinal and the transverse result side thrust, so that the resultant side thrust is 12,565. That should be multiplied with the overall depth of the foundation, because it is acting in the top of the pedestal. So this 3.25 is nothing but the total height which is from the top of the chimney. So this top of the chimney is 300, then 2400 is the depth below the ground until the top of the drop. This 200 is the drop thickness, and this 250 is tapered. 0.1 is a vertical slab thickness. So all this depth we need to consider, because this we are calculating at the toe level of the base slab, and that we are deducting with the concrete weight. Concrete weight, here we need to consider only the wet condition concrete weight for uplift conditions, because we are considering the movement which is caused by the uplift. So the resultant or resisting movement also should be considered about the wet conditions which is occurred, which we can consider for uplift calculations. So these values we already discussed in our first stage of video, so we can look into that how to arrive this value. So that multiplied with the 5 divided by 3, that is 1/3 of the base width. So in total we are getting the total overturning moment is, or the net overturning moment you can say, is 13.7362 kg meter. Similar, like we need to calculate for broken wire condition also. Then total resisting moment. So total resisting moment due to soil we need to calculate. So that is nothing but this picture you can see. The entire mass of the soil which is below the ground level will cause a anti-clockwise movement due to its sulfate filled with the soil, that will act in the 50% of the base width. So we are considering half of the soil density, soil weight into the base slab width. So the soil density we already calculated here in our part 1 video. So in this, the minimum of both the things we need to consider, wet or mass. Most of the case the wet mass will be the maximum, will be the minimum one. So that multiplied that we are getting the total resisting moment as 2342225. So under normal conditions, this equation is very simple. Under normal condition we are dividing this 2342225 with 137362. We are getting 1.71, which is greater than 1. Then hence it is safe in normal conditions. Also for broken wire condition the same, we are doing this. 2342225 divided by 26613, we are getting 8.8, which is also greater than 1. Then this case broken wire condition also safe. So this is what the overturning check. In the next video we will look about the design of chimney. Thank you. Look description for more related videos. Subscribe to this channel for more updates.